Welcome back. In this lecture, we are going to focus on the continuous logistic probability distribution. We denote a logistic distribution with the entire word logistic, followed by two parameters, its mean and scale parameter, like the one for the exponential distribution. We also refer to the mean parameter as the location, and we shall use the terms interchangeably for the remainder of the video. Thus, we read the statement below as, variable y follows a logistic distribution with location 6 and a scale of 3. All right. We often encounter logistic distributions when trying to determine how continuous variable inputs can affect the probability of a binary outcome. This approach is commonly found in forecasting competitive sports events, where there exist only two clear outcomes, victory or defeat. For instance, we can analyze whether the average speed of a tennis player's serve plays a crucial role in the outcome of the match. Expectation dictates that sending the ball with higher velocity leaves opponents with a shorter period to respond. This usually results in a better hit, which could lead to a point for the server. To reach the highest speeds, tennis players often give up some control over the shot, so are less accurate. Therefore, we cannot assume that there is a linear relationship between point conversion and serve speeds. Theory suggests there exists some optimal speed, which enables the serve to still be accurate enough. Then, most of the shots we convert into points will likely have similar velocities. As tennis players go further away from the optimal speed, their shots either become too slow and easy to handle, or too inaccurate. This suggests that the graph of the PDF of the logistic distribution would look similarly to the normal distribution. Actually, the graph of the logistic distribution is defined by two key features, its mean and its scale parameter. The former dictates the center of the graph, whilst the latter shows how spread out the graph is going to be. Going back to the tennis example, the mean would represent the optimal speed, whilst the scale would dictate how lenient we can be with the hit. To elaborate, some tennis players can hit a great serve further away from the optimal speed than others. For instance, Serena Williams can hit fantastic serves, even if the ball moves faster or slower than it optimally should. Therefore, she is going to have a more spread out PDF than some of her opponents. Fantastic. Now let's discuss the cumulative distribution function. It should be a curve that starts off slow, then picks up rather quickly, before plateauing around the 1 mark. That is because once we reach values near the mean, the probability of converting the point drastically goes up. Once again, the scale would dictate the shape of the graph. In this case, the smaller the scale, the later the graph starts to pick up, but the quicker it reaches values close to 1. Okay, you can use expected values to estimate the variance of the distribution. To avoid confusing mathematical expressions, you only need to know it is equal to the square of the scale times pi squared over 3. Great job, everybody. Now that you know all these various types of distributions, we can explore how probability features in other fields. In the next section of this course, we are going to focus on statistics, data science, and other related fields which integrate probability. Thanks for watching.